Good morning, class, and welcome to this lesson on circuits 2, EMF and current. Today, we will be able to define EMF and current. Okay, so pretty simple here. So all batteries, as you can imagine, okay, all batteries have a certain amount of energy that they can produce. Right? All batteries have a certain amount of energy that they produce, distributed amongst a certain amount of charge. Right? So they have a certain amount of energy and distributed amongst a certain amount of charge. And as you can tell from this equation, before, this is the formula for voltage or potential difference. Okay, so certain amount of energy per charge. This is the formula for voltage. So all batteries have a voltage. So for example, this would be a 1.5 volt battery. You have those square batteries. Those look like this. These are 9-volt batteries. Okay, I believe the most batteries in like your phone is like a 3.7-volt battery. Cars have 12-volt batteries. All batteries have a voltage, or a potential difference, and the maximum potential difference, the maximum potential difference of a battery is known as its electromotive force, or EMF. Okay, so if we have a 12-volt car battery, car battery looks something like this. We have a 12-volt car battery. The EMF of the car battery is 12 volts. A 1.5-volt battery the EMF is 1.5 volts. And the symbol for EMF looks something like this. See if I can pull this off. It's going to be kind of difficult. It is a really fancy E. And I believe this is the Greek letter Xi. Okay, I could be wrong about that though. You can correct me if I am. So this is a very fancy looking letter, EMF. All it is the potential difference of the battery, the voltage of the battery. Okay, so if you see these terms, EMF and voltage, these are pretty much synonymous. Okay. Now, we defined EMF. Let's talk about current. Current. Current is defined, okay, as the amount of charge that passes a surface, or that flows through a surface, flows through a surface in a given time. Okay? The amount of charge that flows through a surface in a given time. So this is an imaginary surface inside a wire. How much charge flows through this surface in a given amount of time? So the formula we have for current is I. I is current. I am not sure why. I is current is defined as the change in charge over the change in time. Charge per time. Okay? And this charge per time has a unit of the ampere, or the symbol A for short. So we have amps, which is the definition, which is the symbol, the unit for current. Okay, so current is charge per time, and so just to be somewhat obvious here, if we want to solve for charge, it would be current times time if we have these two symbols. And one thing I want to point out, something I noticed, sometimes they do medical examples, medical problems. Okay, and it'll say how many potassium ions pass a certain point in a given time at this current or something. And so basically what you have to do is you have to solve for delta Q. So you solve for charge, and if it's asking you for how many charges, how many positive K's are passing through a certain point, or how many electrons are passing a certain point. These can be either one or the other. We have to solve for charge first, and once we have charge, we would just divide by the coulombs, 1.6 times 10 to the negative 19th, I think. So So once again, if it's asking for how many ions, how many negatives, how many positives, we would just take the total charge and we would divide by the number for one charge, which is this, and then we would get the number of positives or negatives that we're being asked to solve for. So that's current. Current is the amount of charge that passes through a surface in a given amount of time. Okay, delta Q over delta T.